In this tutorial, we will be discussing balancing nuclear reactions. Let's compare and contrast nuclear and chemical processes first. Chemical reactions involve changes in the electronic structure of the atom. Atoms gain, lose, or share electrons. No change in the nuclei actually occur. Nuclear reactions, however, involve changes in the structure of the nucleus. If the number of protons in the nucleus changes, the atom becomes a different element. If the number of neutrons in the nucleus changes, the atom becomes a different isotope. Nuclear equation is a symbolic representation of the nuclear reaction using nuclide symbols. The radioactive decay of carbon-14 by beta emission is written as this. This is a beta particle, which we'll be talking about later on. Carbon-14 indicates the mass number, which is the protons and the neutrons added together. And the bottom number is the atomic number, which is the protons. The chemical composition of the nuclide is not represented, and the new element is formed as the product along with the type of emission. So, as the beta particle was emission, the atomic number changed, hence carbon changed into nitrogen. The total charge of the conservative sum of the subscripts, the reactant has to equal the product subscripts. And then the superscripts have to equal each other. So notice 234 plus 4 is 238. 90 plus 2 is 92. Think of the arrow as an equal sign. Let's go into the different types of radioactivity before we start doing the actual problems. Alpha decay is a loss of an alpha particle, a helium nucleus. There's 4 over 2. So that means if there's 2 protons here, that means there must be 2 protons up here and 2 neutrons. Alpha particle loses the energy quickly during the interaction. Can be stopped easily by a few pieces of paper due to its large mass and doubled positive charge. It does not normally penetrate lightweight materials such as paper or clothing. It can cause significant damage to a surface of a material or a living tissue due to the great kinetic energy, and causes significant damage to cellular tissue if it's ingested. Electron capture. Addition of an electron to a proton in the nucleus is known as electron capture, or K capture. The result of the process is that a proton is transformed into a neutron. This is not a subatomic particle undergoing decay. No particle emission is emitted, but the atom does change. It occurs in the where an inner orbital electron is pulled into the nucleus. The mass number stays the same, but the atomic number decreases by 1. A similar result is seen with the positron emission. When the electron capture happens, a proton in the nucleus combines with an electron to make a neutron. So therefore the bottom number cancels each other out to make a neutral. The beta decay is a loss of a beta particle, a high energy electron, symboled as this, 0 over negative 1, or 0 over negative 1e. A beta particle is an ejected electron from a neutron. It is not an electron orbiting the nucleus. It's from the nucleus itself. It has a charge of negative 1 and negligible mass, which is why you see 0 up here. Has both a smaller mass and electric charge than the alpha particle and moves faster. It loses energy at a much slower rate in air and travels farther before stopping. Once stopped, it becomes an ordinary electron. It can be stopped with several sheets of aluminum foil or lightweight cloth, and it penetrates fairly deeply into the skin, potential for harming or killing living cells. Some nuclei decay by emitting a positron, a particle that has the same mass as, but an opposite charge of, an electron. So notice here, instead of having a -1 down here, it has a +1. A positron has a charge of a +1 and a negligible mass. It is produced when an atom's proton morphs into a neutron. The mass number remains the same as for the atom, but its atomic number decreases by 1. Remember, if the atomic number changes, the actual element changes. It's referred to as sometimes an anti-electron. Finally, we have gamma rays. Gamma emission is the loss of a gamma ray, which is a high energy radiation that almost always accompanies the loss of a nuclear particle. Gamma rays are high energy electromagnetic radiation emitted when a nucleus is in an excited state moves to a lower energy state. They are more harmful than alpha and beta particles and the most penetrating because they have no mass or charge, just pure energy. They are pure energy, greater per photon than a visible or ultraviolet and X-rays. So let's go through some of these problems. We have K40, so potassium 40, undergoing positron emission. The thing that usually trips people up here is the terminology. So we have K40, so that means we have potassium with a mass of 40. We look on the periodic table and find out that potassium is 19. It's emitting it, so that means it's going to be on the right hand side. We need to make sure that the top numbers and the bottom numbers add up. So 40 is equal to 0 plus x. So our x number up here is 40 again. The bottom number, I'm using the arrow as an equal sign. 19 is equal to 1 plus x. That means it's 18, which gives us argon. The next one, Pu242, so 242, I'm using equals for that arrow, 4 plus x. I subtract 4 to get to x, and that gives me 238. Then the bottom number, 94, is equal to 2 plus x, which gives me 92. I look on the periodic table. I always want to look for that bottom number. I look for 92, and I find that's uranium. The next one, a little bit more difficult. 252 plus x is equal to, notice that 3 here, so we have 3 neutrons. 3 times 1 plus 259. Add and subtract, and that comes out to be 10. The bottom number, 96, plus x is equal to, once again we have that 3 there, 3 times 0 plus 103. Solve for x, and that comes out to be 7. I look for 7 on the periodic table, and I find out that that's nitrogen. And finally, we have x is equal to 32. A beta particle is 0 over -1, so plus 0 on the top. So I have 32 on the top. Then the bottom number is x is equal to 16 plus the bottom number is -1. That gives me 15. Look 15 up on the periodic table, and that's phosphorus. Let's try a few more. Alpha emission. So alpha is 4 over 2 He is emitted from uranium-238. So that means I have uranium-238. I look on the periodic table and I find out that uranium is 92. Alpha is being emitted, so it's a product. And I need to figure out what this last thing is. So 238 is equal to 4 plus something. That gives me 234. Then the bottom number is 92 is equal to 2 plus something. That gives me 90. I look on the periodic table and I find that 90 is TH. Let's do another one. Beta emission. We have neon 24. That number is always going to be your top number. I look on the periodic table and I find that neon is number 10. Emission, once again, it'll be on the right hand side. It's beta 0 over minus 1. You need to memorize what all these symbols mean. Alright, so top number 24 is equal to 0 plus something. That gives me 24. Bottom number 10 is equal to negative 1 plus something. That gives me a number of 11. I look on the periodic table and I find that that's sodium. We're going to do two more. Nitrogen 13. I look on the periodic table and I find that nitrogen is number 7. Positron emission. Emission means it's going on the right. And we're looking for that last thing. So 13 is equal to 0 plus something. That's going to be 13. The bottom number, 7, is equal to 1 plus whatever, x. And that gives me number 6. I look on the periodic table and I find that 6 is carbon. And our last one we're going to be doing, beryllium 7. So that second number here is our top number. We look on the periodic table to find beryllium is number 4. Notice it has the word capture in it this time. It's actually part of the reactants now. 0 over negative 1e is part of the reactants because of the word capture. And that's what I meant by people get caught up in the terminology. Read the questions very carefully and determine if it's going on the left or the right. That trips people up more than the actual math itself. So the top number, 0 plus 7 plus 0 is 7. 4 plus negative 1 is 3. I look on the periodic table and I find that's lithium. And that's how you balance nuclear equations.